Imagine standing at the edge of the universe, staring into the abyss of a black hole, a place so powerful it bends light, warps time, and swallows entire stars without a trace. Now, here's a question that might send shivers down your spine. What happens to everything that falls in? Does it just vanish, or is there something more mysterious at play? This isn't just science fiction, it's one of the most baffling puzzles in modern physics, known as the black hole information paradox. And it's not just about black holes, it's a crisis at the very heart of our understanding of reality itself. For decades, scientists believed that once something crossed a black hole's event horizon, it was gone forever, erased from the universe. But here's the twist: quantum mechanics, the rules governing the smallest particles in existence, insists that information can never truly be destroyed. So which is it? Does the universe have a way of preserving secrets even from the clutches of a black hole? Or are we missing something fundamental about how reality works? This paradox has divided physicists, sparked fiery debates, and even led some to question whether we've been looking at gravity and quantum mechanics all wrong. What makes this mystery so thrilling isn't just the science, it's what it reveals about the nature of existence. If information can escape a black hole, it could rewrite the laws of physics as we know them. Think about it, black holes might not be the ultimate cosmic shredders we once thought. Instead, they could be hiding clues about the fabric of space-time, the origins of the universe, and even the possibility of parallel realities. So buckle up, because we're about to dive into one of the most mind-bending questions in science, one that could change everything we think we know about the cosmos. Are you ready to unravel the mystery? To grasp the mind-bending nature of the black hole information paradox, we first need to understand what black holes actually are. Picture the most extreme prison in the cosmos, a place where gravity doesn't just hold things down, it twists the very fabric of reality. At the heart of every black hole lies an unfathomably dense point called a singularity, where matter is crushed into an infinitely tiny space. Surrounding it is the event horizon, the infamous point of no return. Cross this invisible boundary and there's no coming back, not even for light itself. That's why black holes appear utterly dark. They trap every photon that strays too close. But here's where things get even stranger. Despite their reputation as cosmic vacuum cleaners, black holes aren't entirely black. Thanks to the groundbreaking work of Stephen Hawking, we now know they slowly leak energy through a process called Hawking radiation. This happens when pairs of particles spontaneously pop into existence near the event horizon, as they do everywhere in space. Normally, these particles would annihilate each other instantly, but if one falls into the black hole while the other escapes, the black hole loses a tiny bit of mass over time. It's as if the universe has found a way to make these cosmic monsters slowly evaporate. Yet this revelation only deepens the mystery. If black holes can shrink and eventually vanish, what happens to all the information they swallowed? According to quantum mechanics, every particle, every atom that ever fell in should leave some kind of fingerprint, a trace of its existence. But general relativity, Einstein's theory of gravity, insists that black holes obliterate everything beyond recovery. Two fundamental theories of physics, both incredibly successful in their own domains, give us completely contradictory answers. That's the heart of the paradox. Either our understanding of quantum physics is flawed, or Einstein's gravity needs a radical rewrite, or perhaps both. This isn't just academic, it's a battle for the soul of how we comprehend reality. So why should we care? Because this isn't just about black holes. It's about whether the universe plays by rules that preserve information like an unbreakable code, or if some secrets can truly be lost forever. If Hawking radiation carries no trace of what fell in, then the laws of quantum mechanics, which underpin everything from chemistry to computers, would need a complete overhaul. But if information can somehow escape, it might mean black holes aren't the ultimate dead ends we thought. They could be cosmic vaults hiding answers to questions we haven't even thought to ask yet. Quantum mechanics might sound like an abstract realm reserved for physicists, but its principles are crucial to unlocking the black hole information paradox. At its core, quantum theory operates on a radical idea: information can never truly disappear. This principle, called unitarity, means that if you knew every detail about the present state of a quantum system, you could theoretically rewind time and reconstruct its past or fast forward to predict its future. Think of it like mixing paint. If you blend blue and yellow to make green, the information about the original colors isn't lost, it's just transformed. In theory, you could reverse the process and separate the green back into its components. The universe, at its most fundamental level, seems to play by similar rules. But quantum mechanics doesn't stop there. Particles at this tiny scale can exist in a bizarre state known as superposition, meaning they don't have to choose between being here or there, or even between different properties. An electron, for example, can spin both clockwise and counterclockwise at the same time until you measure it. It's as if reality holds all possible outcomes in limbo until forced to pick one. When we apply this to black holes, things get even weirder. If information is preserved in some quantum superposition, perhaps what falls into a black hole isn't destroyed but simply scrambled, like a cosmic puzzle waiting to be reassembled. Then there's entanglement, one of quantum mechanics' most mind-bending features. When particles become entangled, their properties link in such a way that changing one instantly affects the other, no matter how far apart they are. It's as if two coins, flipped on opposite sides of the galaxy, always land on the same face. This eerie connection might hold the key to how information escapes a black hole. Some theories suggest that particles inside and outside the event horizon could be entangled, creating a hidden bridge that preserves information even as the black hole evaporates. These principles, unitarity, superposition, and entanglement, paint a picture of a universe where information is far more resilient than we ever imagined. But here's the catch: if black holes truly erase information, then quantum mechanics, the very foundation of modern physics, would be fundamentally flawed. That's why this paradox isn't just a curiosity, it's a crisis. Either we're missing something profound about how black holes work, or we've misunderstood the fabric of reality itself. And that's what makes this mystery so electrifying. Solving it could rewrite the rules of the cosmos. At the center of this cosmic mystery lies a fundamental clash between two towering pillars of physics: Einstein's general relativity and the strange rules of quantum mechanics. On one side, general relativity paints black holes as the ultimate cosmic erasers. According to Einstein's equations, once matter crosses the event horizon and reaches the singularity, it's crushed out of existence. Space and time themselves become so warped that the very concept of before and after breaks down. In this view, every star, planet, or hapless spaceship that falls in is reduced to a single, infinitely dense point. No history, no traces, just oblivion. It's as if the universe has a permanent delete button, and black holes wield it without remorse, but quantum mechanics tells a completely different story. In the quantum world, information isn't just useful, it's sacred. The universe operates like a meticulous accountant, keeping track of every particle's spin, position, and energy. Even in chaos, the underlying information never vanishes. It might get scrambled, but it's always recoverable in principle. Imagine dropping a book into a fire. From a classical perspective, the pages turn to ash, gone forever. But quantum mechanics insists that if you could somehow collect every speck of smoke, every ripple of heat, you could theoretically reconstruct the original text. Apply this to black holes and the paradox becomes glaring. How can something that quantum physics says must be preserved get erased by gravity's relentless pull? The tension between these two perspectives isn't just academic, it's a battle for the soul of physics. General relativity excels at explaining the universe on grand scales, from orbiting planets to colliding galaxies. Quantum mechanics dominates the realm of the ultra-tiny, governing atoms and subatomic particles. Both theories have been tested with astonishing precision, yet they offer irreconcilable answers when it comes to black holes. This isn't a minor disagreement, it's a sign that our understanding of reality is incomplete. Some physicists argue the solution lies in bridging the gap between these theories, a so-called theory of everything that unifies gravity and quantum mechanics. Others propose wilder ideas like black holes being holograms, where information isn't lost inside but encoded on their surfaces like a cosmic DVD. Then there are those who suggest that singularities might not be the end at all, that black holes could warp spacetime so severely they birth entirely new universes, carrying the information into another reality. Whatever the truth, one thing is certain: solving this paradox won't just tell us what happens to stuff that falls into a black hole, it'll reveal something profound about the very nature of existence. And that's why this debate isn't just for physicists in ivory towers. It's a glimpse into the deepest workings of the cosmos. Stephen Hawking dropped a bombshell in the 1970s that sent shockwaves through the world of physics. Up until then, most scientists assumed black holes might eventually release whatever they swallowed, even if in some scrambled form. But Hawking's calculations suggested something far more unsettling. Black holes could destroy information completely. Imagine throwing a book into a fire, except the ashes vanish without a trace, leaving no possibility of ever reconstructing the original text. According to Hawking, black holes didn't just hide information behind an inescapable curtain. They erased it from existence, contradicting one of the most sacred principles of quantum mechanics. The implications were staggering. Quantum theory insists that information is indestructible, encoded into the universe like an unbreakable cosmic ledger. Every particle interaction, every collision, leaves some trace behind, even if it's chaotic or dispersed. But Hawking's work suggested black holes could bypass this rule entirely, acting as cosmic shredders that permanently deleted the very fabric of reality's memory. If true, it meant rewriting one of physics' most fundamental laws or accepting that black holes played by entirely different rules. The backlash was immediate and fierce. Some physicists dismissed the idea outright, arguing that Hawking must have made a critical error in his calculations. Others saw it as a challenge, a call to dig deeper into the unknown. The debate became so intense that it earned its own dramatic name, the information loss paradox. Even Hawking himself didn't escape scrutiny. His peers pushed back, demanding proof that information could truly vanish without a trace. Among his most vocal critics was Leonard Susskind, a physicist who argued that if Hawking was right, the foundation of quantum mechanics would crumble. This wasn't just academic squabbling, it was a battle over the nature of reality itself. If black holes could delete information, then the universe wasn't just mysterious, it was fundamentally unpredictable. Laws that governed everything from atoms to galaxies would suddenly have an exception, a cosmic blind spot where causality itself broke down. But the controversy also forced physicists to ask deeper questions. Could Hawking's radiation, the faint glow leaking from black holes, somehow carry hidden imprints of the information swallowed inside? Or was there an entirely new layer of physics waiting to be uncovered? For decades, the paradox remained unresolved, fueling some of the most heated debates in modern science. Hawking himself would later revisit his stance, suggesting that information might escape after all, but the damage was done. The information loss paradox had already exposed a rift in our understanding of the cosmos, one that still challenges physicists today. And that's the beauty of science. Even wrong turns can lead to revelations, forcing us to question, rethink, and ultimately uncover deeper truths about the universe. One of the most radical solutions to the black hole information paradox comes from physicist Leonard Susskind, who proposed that reality might not work the way we think it does. Imagine taking a three-dimensional object like this coffee cup and somehow flattening all its information onto a two-dimensional surface. At first glance, it seems impossible. How could depth, texture, and structure exist without the third dimension? Yet this is the essence of the holographic principle, a mind-bending theory suggesting that all the information inside a black hole isn't lost, it's just projected like a cosmic movie onto its event horizon. Think of the event horizon as a giant, invisible sphere surrounding the black hole, the point of no return. According to Susskind, every particle, every bit of energy that falls in leaves a kind of imprint on this surface. It's as if the black hole's interior isn't where the real action happens. Instead, all the information about what's inside is stored in a two-dimensional code on its outer shell. Picture a hologram sticker. When you tilt it, you see a three-dimensional image, even though all the data is embedded on a flat surface. The universe, it seems, might operate the same way. This idea didn't just solve the paradox, it turned our understanding of space-time upside down. If the holographic principle is correct, then the three-dimensional world we experience could be an illusion, a projection of deeper two-dimensional physics. It would mean black holes aren't destroying information, they're just translating it into another form, one that's preserved forever on their surfaces. Of course, not everyone was convinced. Critics argued that this sounded more like science fiction than hard physics, but the math held up, revealing eerie connections between black holes and quantum theories of information. Even more astonishing, this principle might not just apply to black holes. It could be a fundamental feature of the entire universe. Some physicists speculate that reality itself, from galaxies to human thoughts, might be a holographic projection of underlying two-dimensional data. That's the beauty of Susskind's idea. It doesn't just rescue information from black holes, it hints at a far grander truth. Maybe the universe is like a cosmic hard drive, encoding everything in a hidden layer we're only beginning to decipher. And if that's the case, then black holes aren't cosmic dead ends. They're windows into the deepest secrets of existence. If the holographic principle sounded revolutionary, wait until you hear about AdS/CFT correspondence, a concept so profound it redefines how we think about space, time, and the very nature of reality itself. Born from the depths of string theory, this idea proposes an astonishing link between the inside of a black hole and the information dancing on its surface. Imagine a sealed, windowless room you can't see inside, but every event within leaves a unique mark on the walls. AdS/CFT suggests something similar. The chaotic, warped interior of a black hole, known as anti-de Sitter space, or AdS for short, is perfectly mirrored by a mathematical world living on its boundary, called a conformal field theory, or CFT. Here's where it gets wild. In this framework, the black hole's three-dimensional turmoil, its crushing gravity, its swirling singularities isn't the real story. Instead, all the action is encoded on a two-dimensional surface, like a cosmic movie screen. Think of it as the ultimate compression algorithm. The universe takes everything that happens inside the black hole and flattens it onto its event horizon without losing a single byte of data. It's as if the black hole's entire interior is a hologram projected from information painted on its outer shell. This isn't just a clever metaphor, it's a precise mathematical duality. Every particle falling into the black hole, every twist of spacetime, corresponds to a specific arrangement of quantum fields on the boundary. Even stranger, the two descriptions, the interior and the surface, are completely equivalent. Neither is more real than the other. It's like discovering that a novel and its audiobook, though utterly different in form, contain the exact same story. The implications are staggering. If AdS/CFT holds true, it could solve the information paradox by proving that black holes don't destroy information. They just translate it into another language, one we're only beginning to decipher. But the theory doesn't stop there. Some physicists speculate this correspondence might be a clue to a far grander truth, that our entire universe, with its three spatial dimensions, could itself be a projection of deeper two-dimensional physics. Of course, skeptics question whether this elegant math applies to real-world black holes, which exist in a universe governed by different geometry than the idealized AdS space. Yet, even with these open questions, AdS/CFT has become a playground for theoretical physicists, offering tantalizing hints about how gravity and quantum mechanics might finally reconcile. It's a reminder that sometimes the most universe-shattering answers come from asking not what's inside the black hole, but what's written on its walls. Leonard Suskind's theory of black hole complementarity might sound like a paradox at first, but it's actually a brilliant workaround to the information problem. Picture this: you're an astronaut falling toward a black hole's event horizon. From your perspective, you glide smoothly through that invisible boundary, unaware of any dramatic change. But to an outside observer watching from a safe distance, you appear frozen in time, your image smeared across the horizon like a cosmic fingerprint. Here's the twist: both perspectives are correct. According to Suskind, the laws of physics don't force us to choose between these two realities because no single observer can ever witness both at once. This idea hinges on a fundamental limit in our ability to perceive the universe. Imagine trying to watch a movie from two different angles simultaneously. You'd need to be in two places at once, which is impossible. Black hole complementarity works the same way. The information about what fell into the black hole isn't lost, it's just split into dual descriptions. Inside the horizon, it's part of the black hole's interior. Outside, it's encoded on the surface as a scrambled hologram. But crucially, no observer can ever access both versions to spot a contradiction. Nature, it seems, has built-in privacy settings. What makes this theory so compelling is how it sidesteps the need to rewrite physics entirely. Quantum mechanics can keep its sacred rule: information isn't destroyed, just redistributed. General relativity still holds that black holes warp spacetime beyond recognition. The trick is realizing these truths apply to different vantage points, like parallel stories that never intersect. It's as if the universe has two sets of books for the same event, each accurate in its own context but impossible to reconcile directly. Critics argue this sounds suspiciously like having your cosmological cake and eating it too. If information exists in two places at once, doesn't that violate quantum no-cloning rules? Suskind's response is characteristically clever. No cloning occurs because the two copies are permanently separated by the horizon's one-way barrier. They might as well exist in different universes. This elegant dance of perspectives doesn't just solve the paradox, it reveals something profound about reality itself. Maybe the universe isn't in the business of giving us a single objective truth. Maybe it's built from overlapping layers of truth, each valid within its own frame of reference. That's the genius of complementarity. It doesn't just explain black holes, it suggests that our very notion of what happens might be incomplete without considering who's watching and from where. In a cosmos where gravity bends time and particles blur into waves, perhaps the most fundamental lesson is this: reality isn't just stranger than we imagine, it might be stranger than we can imagine. Just when physicists thought they had a handle on the black hole information paradox, a bombshell dropped in 2012 that turned everything upside down. A team of researchers, Ahmed Olmary, Donald Maroff, Joe Pulczynski, and James Sully, proposed a jaw-dropping scenario now known as the Firewall paradox. Their argument: if quantum mechanics is correct and information really does escape black holes, then the event horizon shouldn't be the gentle boundary we once imagined. Instead, it might be a raging inferno, a wall of high-energy particles so intense it would vaporize anything crossing it. Picture this: you're drifting toward a black hole, expecting to glide smoothly past the event horizon, just as general relativity predicts. But instead of a quiet passage, you're met with a searing blast of radiation, a firewall hotter than the core of a star. This isn't just science fiction. The math suggested that preserving information outside the black hole could demand this violent boundary, shredding the very idea of an uneventful horizon. Suddenly, the elegant solutions like holography and complementarity faced a brutal challenge. If firewalls are real, then Einstein's smooth spacetime near the horizon shatters into chaos. The implications are staggering. Firewalls would mean that black holes aren't just cosmic vacuum cleaners, they're cosmic shredders with built-in incinerators. But here's the catch: this idea clashes head-on with relativity's core principle, the equivalence principle, which states that free-falling observers shouldn't feel extreme forces at the horizon. It's like saying you can't tell you're in a falling elevator until you hit the ground, except now, the ground is a wall of fire. Either quantum mechanics breaks relativity, or we're missing something fundamental about how black holes encode and release information. The debate sparked by AMPS isn't just theoretical nitpicking, it's a battle over the nature of spacetime itself. If firewalls exist, then the event horizon isn't just a point of no return, it's a cosmic executioner. But if they don't, then how does information escape without violating quantum rules? Some physicists argue the answer lies in even wilder ideas, like spacetime being fundamentally pixelated or black holes having fuzzballs instead of singularities. Others suggest that entanglement, the spooky link between particles, might hold the key, creating a subtle bridge that preserves information without the need for fiery drama. What makes the firewall paradox so electrifying is that it doesn't just deepen the mystery, it forces physicists to confront the limits of their theories. Maybe the universe isn't just stranger than we imagined, maybe it's stranger than our current math can describe. And that's the heart of science. Every answer births new questions, pushing us closer to truths we can't yet see. Whether firewalls are real or just a red herring, one thing's certain: the black hole information paradox is far from solved, and the next breakthrough could rewrite reality as we know it. Quantum entanglement and wormholes might sound like they belong in separate realms of physics, one ruling the subatomic world, the other bending the fabric of spacetime. But what if these two bizarre phenomena are secretly intertwined? Enter the ER equals EPR conjecture, a daring idea that suggests quantum entanglement and Einstein-Rosen bridges, better known as wormholes, might be two sides of the same cosmic coin. Imagine two particles entangled across the universe, instantly influencing each other no matter the distance. Now picture a wormhole, a tunnel through spacetime connecting those same particles. According to this theory, they're not just similar, they're fundamentally the same. This isn't just poetic symmetry, it's a radical rethinking of how information could escape a black hole. If entangled particles are linked by microscopic wormholes, then the information swallowed by a black hole might not be trapped inside. It could be threaded through spacetime itself, woven into the quantum foam that underpins reality. Think of it like a secret passage in a castle. From the outside, the walls look impenetrable, but there's a hidden route that bypasses the barriers entirely. In this case, the castle is the black hole, and the passage is a web of entanglement connecting what's inside to what's outside. The implications are staggering. It would mean that black holes don't just preserve information on their surfaces, as holography suggests, they might also broadcast it through spacetime's hidden tunnels. Picture a pair of entangled particles near a black hole's event horizon. One falls in, the other escapes. Normally, their link would seem severed, but if entanglement creates a wormhole, that connection persists. The information inside the black hole could flow through this invisible bridge, emerging subtly in the radiation leaking outward. It's as if the universe has built-in escape routes, ensuring no data is ever truly lost. Critics argue this idea blurs the line between metaphor and physics. After all, wormholes are solutions to Einstein's equations, while entanglement is a quantum quirk. Bridging them requires a theory that unites gravity and quantum mechanics, which we still lack. Yet the math hints at something profound. In certain simplified models, the equations describing entanglement mirror those describing wormholes, as if nature is hinting at a deeper connection. It's like discovering two entirely different languages somehow encode the same story. Whether this conjecture holds up or not, it underscores a thrilling possibility. The fabric of space-time might be stitched together by quantum entanglement. Black holes, far from being cosmic dead ends, could be hubs in a vast network of hidden connections. And if that's true, then the information paradox isn't just a puzzle. It's a clue pointing toward a grander theory of everything, where space-time, gravity, and quantum weirdness finally unite. The universe, it seems, has been playing a game of hide and seek with its deepest secrets, and we're only just beginning to peek behind the curtain. String theory has always danced on the edge of the known and the unimaginable, but its take on black holes might be its most radical idea yet. Forget the infinitely dense singularity at the heart of a traditional black hole. Picture instead a swirling, vibrating knot of cosmic strings, a fuzzball as physicists call it. This isn't just a poetic name, it's a complete reimagining of what a black hole could be. According to this theory, black holes aren't empty pits with event horizons hiding a singularity. They're dense, fuzzy spheres made entirely of tangled strings, the same fundamental threads that string theory claims make up all matter and energy in the universe. The fuzzball concept flips the script on the information paradox. Instead of information vanishing into a singularity, it's preserved in the chaotic vibrations of these strings on the fuzzball surface. Think of it like a symphony where every instrument's note encodes a piece of data. Even if the music sounds chaotic, the information isn't lost, it's just intricately woven into the performance. In the same way, the strings on a fuzzball's surface vibrate in incredibly complex patterns, storing every bit of information about what fell into the black hole. There's no need for a mysterious singularity or a destructive firewall. The data is right there, humming away on the surface. This idea didn't come out of nowhere. String theory has long suggested that the fundamental building blocks of reality aren't point-like particles but tiny, vibrating strings. When applied to black holes, this led to a stunning realization. If strings can't be squeezed into a single point, then singularities can't exist. Instead, the immense gravity of a black hole would stretch and twist these strings into a dense, fuzzy ball with no sharp boundary or interior void. The event horizon, in this view, isn't a one-way gate, it's the outer layer of the fuzzball itself, pulsing with encoded information. Critics argue that fuzzballs raise their own questions. How exactly do these vibrations translate into the information we observe? And if black holes are solid objects, why do they still behave like perfect traps for light and matter? Supporters counter that the math aligns beautifully with quantum mechanics, avoiding the paradoxes that plague traditional black hole models. Plus, fuzzballs eliminate the need for information to escape at all. It never gets swallowed in the first place, just rearranged. What's truly mesmerizing about this theory isn't just its solution to the information paradox, it's how it reframes black holes from cosmic trash compactors into dynamic, vibrating entities. They're not graveyards for information, they're libraries storing data in a language we're only beginning to decipher. And if string theory is correct, these fuzzballs might be the key to unlocking a deeper truth, that the universe's most extreme objects aren't exceptions to the rules, they're expressions of them writ large in the fabric of spacetime. Stephen Hawking's final twist in the black hole information saga might be his most elegant, yet a concept called soft hair. Picture this: every time something falls into a black hole, it doesn't just vanish without a trace. Instead, it leaves behind faint ripples in space-time, like whispers etched into the fabric of the universe. These aren't dramatic scars or fiery imprints. They're delicate, almost ghostly patterns known as soft quantum hairs. And according to Hawking, these subtle markings could be the key to preserving information without violating any laws of physics. The idea builds on a peculiar feature of gravity itself. When particles cross a black hole's event horizon, they disturb the surrounding space-time in a way that creates zero-energy vibrations, so gentle they're called soft particles. Unlike the high-energy chaos of Hawking radiation, these vibrations don't carry measurable energy, but they do carry something far more precious: data. Imagine dragging your hand through a still pond. The water barely moves, but the ripples hold the memory of your touch. Soft hairs work the same way, encoding details about what fell into the black hole in nearly imperceptible space-time waves. This wasn't just a poetic notion, it was a mathematical breakthrough. Hawking and his collaborators showed that these soft hairs could store information in the black hole's gravitational field, like cosmic barcodes etched into the event horizon. Even as the black hole evaporates over eons, those imprints remain, subtly altering the pattern of radiation that escapes. It's as if the universe has a fail-safe. When destruction seems inevitable, it hides clues in the quietest places imaginable. Critics, of course, raised eyebrows. Can such faint imprints really preserve the intricate details of a fallen star or a swallowed spaceship? And if so, how could we ever decode them? Supporters argue that the math holds up, and that soft hairs offer a middle ground between the brutality of firewalls and the abstraction of holography. Instead of tearing space-time apart or projecting reality onto a surface, this solution lets information linger in the fabric of gravity itself, a natural extension of Einstein's vision. What makes soft hairs so captivating isn't just their potential to solve the paradox. It's how they embody Hawking's lifelong quest to reconcile the large and the small, the violent and the subtle. Black holes might be the universe's most destructive forces, but they could also be its most meticulous archivists, keeping records in a language written on space-time itself. And if that's true, then the answer to the information paradox wasn't hidden in explosions or holograms, it was hiding in plain sight, woven into the quietest whispers of gravity. If black holes are cosmic vaults hiding information, the burning question remains: when does that data finally break free? Enter Don Page, a physicist who tackled this puzzle with a startling calculation. His work reveals something counterintuitive. Information doesn't seep out slowly over a black hole's lifetime. Instead, it stays locked away until the black hole has evaporated past the halfway point, like a time-released capsule that only cracks open after eons of patient waiting. Think of a black hole's life as an hourglass. For the first half, sand flows steadily downward, representing the slow loss of mass through Hawking radiation. But here's the twist. During this phase, the radiation carries no useful information. It's pure thermal noise, like static on a radio. Only when the hourglass is more empty than full does the signal finally emerge from the noise. Page's math showed that the quantum correlations encoding information simply can't surface until the black hole has shed enough of its mass. It's as if the universe enforces a cosmic embargo, refusing to reveal its secrets until the very last act. This delayed release isn't just a quirk of the math, it's a survival mechanism for quantum mechanics. If information leaked out too soon, it could create paradoxical duplicates, violating quantum no-cloning rules. By holding back until the black hole is sufficiently diminished, the universe avoids breaking its own laws. Picture a chef carefully reducing a sauce. The flavors only concentrate when most of the water has evaporated. Similarly, black holes only reduce their information into detectable form late in their evaporation. Critics questioned whether this timeline aligns with real-world observations. After all, the largest black holes take longer than the current age of the universe to evaporate even slightly. So how could we ever test this? Page's response was pragmatic. The math doesn't lie. Whether we witness it or not, the universe seems to follow these rules, ensuring information survival even in the most extreme conditions. What makes Page's calculation so profound is its quiet elegance. No firewalls, no holograms, just a simple, inevitable timeline where information waits patiently for its moment. It suggests that black holes aren't just chaotic destroyers but meticulous archivists, guarding their secrets until the universe itself demands their return. And that's the beauty of physics. Sometimes the answers aren't flashy. They're written in the steady, unyielding language of mathematics, whispering truths across the fabric of space-time. Quantum Darwinism offers a fresh lens to understand how information might escape the grasp of a black hole, not through brute force but through a cosmic game of survival of the fittest. Picture a quantum world where countless possible states exist simultaneously, like a tree with infinite branching paths. Most of these states vanish almost instantly, collapsing into oblivion. But a select few get replicated, amplified, and spread into the environment, much like how only the fittest traits persist in biological evolution. In the chaotic maelstrom near a black hole's event horizon, this process could determine which fragments of information make it out and which are lost forever. The key lies in what physicists call pointer states, special quantum configurations robust enough to withstand decoherence, the process where quantum weirdness gets washed away by interaction with the environment. Near a black hole, particles and their quantum states are constantly buffeted by extreme gravity, Hawking radiation, and space-time curvature. Most states crumble under these forces, but pointer states endure, imprinting themselves onto the outgoing radiation. It's as if the black hole's surroundings act as a sieve, filtering out fragile quantum information while letting the most resilient data slip through. This idea flips the script on traditional survival narratives. Instead of information being passively scrambled or encoded, it actively competes for a chance to escape. Imagine tossing a handful of papers into a storm. Some shred instantly, while others, made of sturdier material, survive the winds and land intact. Quantum Darwinism suggests the universe operates similarly, with the environment acting as both destroyer and curator. The information we detect in Hawking radiation might not be a random sampling. It could be the subset that was fit enough to replicate and persist. Critics argue this raises thorny questions. Who or what decides which states are fittest? Is the environment near a black hole truly selective enough to mimic Darwinian processes? Proponents counter that no conscious selector is needed. The laws of physics alone favor states least disrupted by decoherence. Just as natural selection shapes life without a guiding hand, quantum Darwinism could shape information escape without any cosmic referee. What's fascinating is how this bridges the microscopic and the macroscopic. At the quantum level, countless possibilities flicker in and out of existence, but at the scale we observe, only certain patterns stabilize and become measurable. In a black hole's deadly embrace, this might mean that the information we eventually recover isn't a full snapshot, it's a highlight reel of the most durable quantum imprints. This perspective doesn't just solve a paradox, it reshapes how we think about reality itself. Maybe the universe isn't just preserving information, it's constantly editing it, favoring coherence over chaos. And if that's true, then black holes aren't just traps or tunnels. They're quantum colosseums where information battles for immortality, and only the strongest signals survive to tell the tale. Gravitational waves ripple through space-time like cosmic sonar, carrying whispers of the universe's most violent collisions. When black holes merge, they don't just vanish into silence, they ring like bells, sending out waves that detectors like LIGO can catch. But what if those waves hold more than just the story of a collision? Recent research suggests these gravitational echoes might carry something astonishing, faint imprints of the information thought to be locked inside black holes. It's as if the universe leaves breadcrumbs in the aftermath of chaos, clues hidden in the very fabric of space-time. The idea hinges on the ring-down phase, the final moments after two black holes collide. Like a struck gong, the newly merged black hole vibrates, emitting gravitational waves that gradually fade. Normally, these waves align perfectly with Einstein's predictions, smooth, clean, and devoid of any hidden messages. But some physicists argue there could be subtle deviations, tiny echoes riding the gravitational waves like ripples bouncing off the walls of a cave. These echoes, if they exist, might betray the presence of quantum structures near the event horizon structures that could encode information about what the black hole swallowed. Imagine dropping a pebble into a pond. The initial splash is predictable, but the ripples that reflect off rocks or branches carry hints about the pond's hidden features. Similarly, if a black hole's event horizon isn't the perfect boundary, relativity suggests if it's fuzzy or lined with quantum effects, those imperfections could scatter gravitational waves, creating faint echoes in the data. These wouldn't just be noise, they'd be a fingerprint of the black hole's interior, a way for trapped information to signal its presence from beyond the horizon. Critics caution that these echoes might be mirages, artifacts of data analysis rather than true physics. After all, gravitational wave detectors are pushing the limits of technology, and teasing out such subtle signals is like listening for a whisper in a hurricane. But proponents point to tantalizing anomalies in some LIGO observations, hints of extra wiggles in the ring-down phase that don't quite match standard models. Could these be the first murmurs of escaping information, or just statistical flukes? The debate is fierce, and the stakes couldn't be higher. If echoes are real, they'd offer a direct window into quantum gravity, a theory that's eluded physicists for a century. What makes this search so electrifying is its audacity. We're not just peering at black holes, we're listening to them, decoding their final vibrations for encrypted messages. It's a cosmic detective story where the clues are written in spacetime itself. And if those echoes hold even a fraction of the promise some theorists believe, they could rewrite our understanding of where information goes when it crosses the point of no return. Not lost, not destroyed, but vibrating silently in the aftermath of the universe's most violent symphonies. Quantum computers might seem like an unlikely tool for cracking the mysteries of black holes, but they're offering physicists something unprecedented, a digital playground to simulate the impossible. Unlike classical computers that struggle with the mind-bending math of quantum gravity, these machines thrive in chaos, mimicking the behavior of particles near an event horizon with startling accuracy. Take IBM's recent experiments, where researchers programmed qubits to act like entangled particles near a simulated black hole. The results, hints that information might not vanish after all, it could scramble in ways we're only beginning to decode. Here's how it works. Imagine rebuilding a black hole's information paradox in miniature, using qubits as stand-ins for particles falling into the abyss. In one experiment, scientists entangled qubits to represent pairs of particles, one crossing the event horizon, the other escaping as radiation. As the simulation ran, the team watched for clues in the quantum noise. Remarkably, patterns emerged suggesting that even as information seemed lost in the simulated black hole, traces of it lingered in the correlations between qubits. It's like burning a piece of paper but discovering its text mysteriously reappears in the smoke. These simulations aren't just academic exercises, they're testing grounds for theories too complex for pencil and paper math. For instance, some models predict that black holes scramble information like a cosmic blender, mixing it so thoroughly it becomes unrecognizable. But quantum computers reveal a twist. This scrambling might follow precise, hidden rules. In certain simulations, information doesn't just randomize, it spreads in fractal-like patterns, echoing the holographic principle's claim that data isn't lost but redistributed. Yet challenges remain. Current quantum computers are noisy, prone to errors that can skew results. Simulating even a tiny black hole requires thousands of qubits, far beyond today's hardware. But the promise is undeniable. Each experiment nudges us closer to answering whether Hawking radiation carries hidden imprints of what fell in, or if space-time itself has backup mechanisms we've yet to imagine. What's thrilling isn't just the potential answers, it's the method. For the first time, we're not just theorizing about black holes, we're recreating their quirks in machines that think in quantum. And every glitch, every unexpected result, might be a clue pointing toward the ultimate reconciliation of gravity and quantum mechanics. Whether these simulations confirm holography, complementarity, or something entirely new, one thing's clear. The future of black hole physics isn't just in telescopes or equations, it's in the entangled whispers of qubits. What if black holes aren't the end of the story, but the beginning? The baby universe hypothesis dares to suggest that when information vanishes beyond the event horizon, it doesn't disappear, it becomes the seed for an entirely new cosmos. Picture a cosmic matryoshka doll, where every black hole in our universe might contain a fledgling reality of its own, expanding in dimensions we can't perceive. This isn't just wild speculation, it's a radical solution to the information paradox, one that rewrites black holes from cosmic graveyards into cosmic cradles. The idea builds on a peculiar property of Einstein's equations. At the heart of a black hole, gravity doesn't just crush matter, it warps space-time so severely that the usual rules of physics break down. Some interpretations suggest this singularity isn't a dead end but a gateway, a place where space-time pinches off and reconnects to a new region of existence. Think of it like a bubble forming in boiling water. Our universe's black hole might be the stem, while the interior inflates into its own separate space-time, complete with its own laws and constants. Information swallowed by the black hole wouldn't be destroyed, it'd be reborn as the raw material for this newborn universe. Supporters of this theory point to eerie parallels with cosmic inflation, the process that launched our own universe into being. Just as a tiny speck of energy exploded into everything we see today, a black hole's singularity might trigger a similar expansion, only this time hidden behind an event horizon. The math even hints that these baby universes could inherit subtle traits from their parent, like quantum fingerprints embedded in their initial conditions. It's as if every black hole is writing a will, bequeathing its information to a reality we'll never see. Critics, of course, raise practical hurdles. If universes spawn inside black holes, how could we ever detect them? And what stops this process from spiraling into infinite regress universes within universes, ad infinitum? Yet the hypothesis has a poetic elegance. It transforms black holes from information shredders into cosmic storytellers, passing narratives across existential boundaries. Perhaps the reason we can't find lost information in our universe is because it's not lost at all, it's just thriving elsewhere, in a reality where our black hole's crushing grip is its Big Bang. What's mesmerizing about this idea isn't just its audacity, it's how it reframes destruction as transformation. A dying star's collapse, a galaxy's feast on matter, these aren't endings but portals. Even Hawking radiation, the faint glow of evaporating black holes, might carry echoes of those infant universes, like distant radio signals from a shore we'll never reach. Whether the baby universe hypothesis holds up or not, it reminds us that in the cosmos, nothing truly ends. It just becomes part of a story too vast for us to read yet. What if the solution to the black hole information paradox isn't about escaping or encoding but rewriting the rules themselves? One of the most radical proposals in physics suggests that when particles reach the crushing depths of a singularity, quantum mechanics doesn't break, it reboots. This idea, known as forced quantum resets, dares to imagine that the universe has a built-in failsafe, At the moment of infinite density, the laws of physics briefly morph to ensure no information is ever truly lost. Think of it like a cosmic Control-Alt-Delete. When the system crashes, it doesn't erase the data. It forces a restart that preserves every crucial bit. At first glance, this sounds like cheating an ad hoc fix to a stubborn problem, but dig deeper and the math reveals something startling. Singularities aren't just points of infinite density, they're boundaries where space-time itself dissolves. In such extreme conditions, quantum mechanics might not just falter, it could evolve. Proponents argue that near the singularity, quantum states don't collapse chaotically. They reset into new configurations that retain their original information, like a scrambled jigsaw puzzle reassembling itself by an invisible hand. This wouldn't violate quantum laws, it would temporarily bend them, creating a protective bubble where information survives despite the surrounding annihilation. Critics pounce on this as wishful thinking. If physics can rewrite itself under pressure, doesn't that undermine the predictability of the entire universe? Supporters counter with an analogy. Water behaves predictably until it boils, when its molecules suddenly transition to gas. Similarly, quantum mechanics might have a phase transition at singularities. A shift so drastic it looks like magic from the outside, but remains governed by deeper, undiscovered laws. The key insight: information isn't destroyed, it's transformed into a language the singularity can't silence. What's electrifying about this idea isn't just its audacity, it's the doors it opens. If forced quantum resets are real, they'd imply that black holes are cosmic laboratories where the universe stress tests its own rules. Every singularity becomes a crucible, forging new physics in its wake. Maybe the information paradox isn't a problem to solve, but a clue that quantum mechanics, as we know it, is just the first draft of a far grander theory. And if that's true, then black holes aren't just swallowing stars, they're rewriting the script of reality itself. Testing these mind-bending theories about black holes faces one enormous hurdle. We're trying to study the universe's most extreme environments from billions of miles away with technology that's still catching up to our curiosity. Think about the challenge. A typical black hole's event horizon could be smaller than a city, yet it warps space-time so severely that light itself can't escape. How do you observe something that actively swallows the very signals, light, radio waves, X-rays we rely on to study cosmic objects? It's like trying to map the interior of a cave by tossing in flashlights that instantly turn off when they cross the entrance. Our current tools do give us glimpses, but they're frustratingly indirect. Telescopes like the Event Horizon Telescope captured that now iconic image of M87's black hole shadow, a donut of light bending around the abyss. But that's just the silhouette of the event horizon, not the chaotic interior where information might be scrambling or escaping. Even gravitational wave detectors, which hear the ripples from black hole collisions, only sense the before and after of mergers, like listening to a conversation through a thick wall. The crucial moments when information could be leaking out, those happen behind a curtain we can't lift. Then there's the timescale problem. A stellar mass black hole takes trillions of years to evaporate via Hawking radiation, far longer than the universe has existed. So waiting to catch one in its final stages, when page calculations suggest information might emerge, isn't just impractical, it's impossible. Even simulations face limits. Supercomputers modeling quantum gravity must simplify realities, and lab experiments using sound waves or light to mimic event horizons are just rough analogies. It's like trying to understand a hurricane by studying a spinning teacup. And yet, perhaps the biggest obstacle isn't technical, it's conceptual. Many theories about information escape, from holography to baby universes, rely on physics we haven't yet discovered, like a full quantum gravity theory. Without it, we're like detectives with half the clues, piecing together a story where the most critical pages are missing. That's why breakthroughs might require more than better telescopes. They'll demand leaps in fundamental physics, perhaps even new mathematics, to describe what happens where relativity and quantum mechanics collide. For now, black holes guard their secrets fiercely, but every constraint is also a guidepost. The very difficulty of testing these ideas pushes us toward more creative experiments, whether probing quantum gravity with tabletop experiments or scouring gravitational waves for hidden echoes. After all, the universe doesn't owe us easy answers. Sometimes the deepest truths hide in the places hardest to reach. The next generation of gravitational wave detectors might hold the key to unlocking one of physics' greatest mysteries: how information escapes a black hole. While LIGO has already revolutionized our understanding of cosmic collisions, future upgrades and entirely new observatories could peer deeper into the chaos of merging black holes, hunting for subtle anomalies that betray the presence of hidden quantum data. Imagine listening to the reverberations of a colossal bell, except instead of sound, these vibrations ripple through space-time itself, carrying encrypted messages from beyond the event horizon. Upcoming detectors like the Einstein telescope and Cosmic Explorer will be exponentially more sensitive, capable of picking up gravitational waves from mergers billions of light-years away. But it's not just about distance. These machines will capture finer details in the ring-down phase, the final moments when the merged black hole settles into its new shape. Traditional relativity predicts a smooth, clean signal, but if quantum effects near the horizon alter spacetime's behavior, whether through holographic imprints, fuzzballs, or hidden wormholes, those deviations could manifest as faint echoes or distortions in the gravitational waves. Picture a flawless musical note with an almost imperceptible warble. That tiny imperfection might encode the universe's best-kept secret. Some theorists speculate that quantum entanglement, the spooky link between particles, could leave its mark on these waves. When black holes merge, the violent disruption of their event horizons might briefly expose entangled particles stranded on opposite sides, imprinting a telltale signature on the outgoing radiation. Others suggest that if information is stored on the horizon's surface, as holography claims, the colossal energy of a merger could momentarily shake loose some of that data, like dust dislodged from a rug. Future detectors, tuned to precision beyond anything we've achieved, might catch these whispers in the gravitational static. Of course, the challenge is staggering. Distinguishing quantum imprints from mundane noise requires isolating signals smaller than the quantum fluctuations of the detectors themselves. It's like trying to hear a single raindrop in a thunderstorm. Yet recent advances in quantum squeezing, a technique that manipulates light at subatomic scales to reduce measurement uncertainty, could tip the scales in our favor. Pair that with AI-driven data analysis capable of spotting patterns invisible to human researchers, and suddenly the impossible starts to look plausible. What makes this quest so electrifying isn't just the potential discovery, it's the sheer audacity of the method. We're not just observing black holes, we're eavesdropping on their quantum murmurs, searching for cracks in Einstein's pristine spacetime. If successful, we won't just solve the information paradox, we'll prove that even the universe's most impenetrable vaults have leaks, and gravity itself has been keeping score all along. The black hole information paradox isn't just a puzzle, it's the ultimate proving ground for a theory that's eluded physicists for over a century: quantum gravity. Think of it as the universe's most extreme laboratory, where Einstein's general relativity and quantum mechanics, the twin pillars of modern physics, are forced into a showdown. On one hand, relativity paints black holes as smooth, geometric beasts, warping spacetime with mathematical elegance. On the other, quantum mechanics insists that information can never be destroyed, clinging to existence with subatomic stubbornness. The paradox emerges where these two frameworks collide, revealing cracks in our understanding so profound they demand a revolution. This isn't just academic curiosity. Uniting relativity and quantum mechanics would answer fundamental questions about the fabric of reality, how space-time behaves at the smallest scales, whether singularities truly exist, or if the universe operates like a cosmic quantum computer. String theory, loop quantum gravity, and emergent gravity models all offer potential solutions, but black holes are their crucible. Take string theory's fuzzballs. If black holes are tangled knots of vibrating strings, their event horizons become dynamic surfaces teeming with quantum data. Loop quantum gravity, meanwhile, suggests spacetime might be pixelated at the tiniest scales, preventing singularities from forming altogether. These ideas aren't just speculative, they're testable in principle, using black holes as nature's particle accelerators. The stakes couldn't be higher. If quantum gravity resolves the paradox by showing how information escapes, it would validate decades of theoretical work. But if it fails, if black holes truly erase information, then quantum mechanics, the foundation of everything from chemistry to computing, might need a radical rewrite. It's like discovering a flaw in the blueprint of reality itself. That's why physicists treat black holes as more than cosmic oddities. They're Rosetta Stones, decoding the hidden language that binds the universe's largest and smallest scales. What makes this quest so electrifying is its sheer audacity. We're not just stitching together two theories, we're probing the limits of knowledge, testing ideas in realms where time loops, space fractures, and matter dissolves into pure mathematics. And every breakthrough, whether it's a whisper in gravitational waves or a glitch in quantum simulations, brings us closer to a truth that could redefine existence. The paradox isn't a dead end, it's a gateway, and on the other side lies a theory waiting to rewrite the cosmos. Black holes might seem like cosmic voids where chaos reigns supreme, but there's an unexpected twist. They're also masters of order, governed by precise thermodynamic laws. This revelation came when Jacob Bekenstein and Stephen Hawking made a startling connection. Black holes don't just consume matter and energy, they possess entropy, a measure of hidden information. It's as if these gravitational monsters are less like shredders and more like librarians, meticulously cataloging everything they swallow in ways we're only beginning to decipher. Entropy, in everyday terms, is the universe's way of tracking disorder. Think of a deck of cards shuffled into randomness, but for black holes, entropy takes on a deeper meaning. Bekenstein realized that the surface area of a black hole's event horizon isn't just a boundary, it's a ledger. The larger the horizon, the more entropy the black hole contains and the more information it conceals. Hawking then took this further, showing that black holes aren't just cold, static graves, they have temperature, radiating energy through quantum effects. Together, their work birthed the Bekenstein-Hawking formula, which ties a black hole's entropy directly to the size of its event horizon. Every square Planck length of that surface, it turns out, can store roughly 1 bit of quantum information. This insight flipped the script on how we view black holes. Instead of being information destroyers, they might be the universe's most efficient scramblers. Picture throwing a book into a blender. The pages are torn apart, but every word still exists in the resulting pulp. Similarly, a black hole could churn and twist the information it consumes, spreading it across its horizon in a chaotic yet perfectly preserved pattern. The information isn't lost, it's transformed into a language written in the geometry of spacetime itself. The implications are staggering. If black holes obey thermodynamic laws, they're not just celestial anomalies, they're part of a grander cosmic balance. Just as heat flows from hot to cold, information might flow into and out of black holes in ways that preserve the universe's quantum rulebook. This doesn't just solve the information paradox, it suggests that the fabric of reality has built-in safeguards, ensuring no data ever truly vanishes. Critics, of course, raise questions. How exactly does information encoded on a horizon translate back into recognizable form? And if black holes evaporate over eons, what happens to the data they've scrambled? Supporters point to holography, where the horizon's two-dimensional surface holds a complete, if jumbled, record of the three-dimensional interior. It's like compressing a movie into a barcode. The full story is there, just waiting to be unpacked. What makes this discovery so profound isn't just the math, it's the philosophical shift. Black holes, once seen as the universe's ultimate endpoints, might actually be its most sophisticated archivists. They challenge us to rethink not just gravity or quantum mechanics, but the very nature of information itself. And if that's true, then the cosmos isn't just a collection of stars and galaxies, it's a vast, dynamic network where even the darkest voids are whispering secrets in the language of entropy. Roger Penrose once proposed a fascinating idea: nature might be protecting us from its own extremes. His cosmic censorship hypothesis suggests that singularities, those infinitely dense points at the heart of black holes, are always hidden behind event horizons, never exposed to the outside universe. Think of it as a cosmic magician's trick. The most violent, law-breaking regions of spacetime are carefully tucked away behind an invisible curtain. Without an event horizon shielding us, a naked singularity, one not cloaked by a black hole's shadow, would wreak havoc on reality as we know it. Cause and effect would crumble, physics would lose predictability, and the universe as we understand it might not make sense at all. This isn't just about black holes playing coy, it's about stability. Exposed singularities would allow information, or even entire chunks of spacetime, to vanish or reappear without warning, like glitches in the fabric of existence. Nature, it seems, has no tolerance for such chaos. By confining singularities behind horizons, the universe enforces a kind of cosmic law and order. No matter how violent the collapse of a star, no matter how much matter gets crushed into an infinitely small point, the damage is contained. The event horizon acts like a one-way prison wall, preventing the singularity's paradoxes from leaking into the wider cosmos. But here's where things get thorny. If singularities are permanently hidden, how does that square with the information paradox? If everything that falls into a black hole gets funneled to an unreachable singularity, doesn't that mean information is lost forever? Penrose's idea seems to side with general relativity, that singularities are where the rules of physics break down completely. Yet quantum mechanics insists information can't just disappear. So is cosmic censorship helping preserve the universe's structure at the cost of quantum lawfulness? Some theorists argue that cosmic censorship and information preservation might not be in conflict after all. If the event horizon isn't just a barrier but a dynamic surface, like the holographic principle suggests, then even while the singularity remains hidden, information could still be etched onto the horizon's fabric. Others speculate that singularities might not be the dead ends we think they are. Could they be gateways or even quantum error correction mechanisms, ensuring information isn't lost but transformed? The beauty of cosmic censorship is how it frames black holes not as cosmic mistakes but as safeguards. They're the universe's way of handling its own worst-case scenarios, keeping the chaos of infinite density locked away. Yet the paradox lingers, reminding us that even nature's most elegant solutions might only be temporary fixes. Maybe the answer isn't choosing between censorship and preservation, but discovering a deeper rule where both coexist, one where the universe hides its most dangerous secrets but never lets them truly disappear. Black holes might be more than cosmic vacuum cleaners. They could be the universe's oldest libraries, safeguarding ancestral information like a cosmic DNA. Imagine every star, planet, or speck of dust swallowed by a black hole doesn't just vanish, it's etched into the fabric of spacetime itself, preserved in a language we're only beginning to decipher. This isn't just poetic speculation, it's a haunting possibility that black holes serve as cosmic hard drives, encoding the history of everything they've ever consumed. Think of it like this: when a tree falls in a forest, its rings tell the story of every storm, drought, and season it endured. Black holes might function similarly, their event horizons bearing intricate imprints of every object that crossed them. The difference, instead of tree rings, the data is written in quantum bits, scrambled across the horizon's surface like a celestial jigsaw puzzle. Some theories even suggest that the universe's earliest moments, its childhood, if you will, could be locked inside primordial black holes forged in the chaos of the Big Bang. These ancient anomalies wouldn't just be relics, they'd be time capsules holding blueprints of a younger cosmos. The idea gains traction when you consider how black holes interact with time. Near a singularity, gravity warps clocks to a standstill, stretching seconds into eons. Information falling in could be suspended, frozen in a state that outlasts the lifespan of stars. It's as if black holes don't destroy the past, they archive it, compressing entire histories into quantum code. And just like DNA dictates the blueprint of life, this cosmic data might influence the larger universe in ways we can't yet see. Could the gravitational ripples from merging black holes carry echoes of their memories? Might the Hawking radiation emitted by dying black holes contain fragments of ancestral fire, like embers from a forgotten forge? Skeptics argue that without a clear mechanism to retrieve this data, the analogy breaks down. After all, DNA is readable. Black hole information is scrambled beyond recognition. Yet proponents counter that the universe often hides its deepest truths in complexity. The very fact that black holes obey thermodynamic laws, that they have entropy, temperature, and even a kind of quantum hair, hints at an underlying order beneath the chaos. If we could crack the code, we might not just solve the information paradox, we could glimpse the universe's origin story, tucked away in the darkest corners of existence. What's mesmerizing isn't just the science, it's the implication. If black holes really are cosmic archivists, then the universe isn't just expanding, it's remembering. Every collision, every meal, every burst of radiation could be part of a vast, interconnected ledger, documenting reality's twists and turns. And while we're far from decoding that ledger, the mere possibility transforms black holes from celestial monsters into something far more profound, keepers of the cosmos's deepest secrets, waiting patiently for us to learn their language. Imagine a future where we don't just study black holes, we harness them. If we could decode the quantum language in which black holes store information, we might unlock technologies that sound like pure science fiction today. Take quantum computing right now. Our most advanced quantum processors struggle with noise and decoherence, their fragile qubits collapsing at the slightest disturbance. But black holes, they've been flawlessly preserving and processing quantum information for billions of years. By reverse engineering how event horizons scramble data without destroying it, we could design error-proof quantum memory systems where information self-corrects, protected by the same physics that keeps black hole data intact across cosmic timescales. This isn't just about better computers. The holographic principle suggests spacetime itself might operate like a quantum code. If true, we could manipulate reality at its most fundamental level, engineering spacetime like software. Picture gravity batteries that store energy in artificially induced spacetime curvatures, or communication networks that exploit quantum entanglement bridges across wormholes. The Alcubierre warp drive, often dismissed as fantasy, might become feasible if we learn how black holes bend spacetime so severely without breaking. We wouldn't just be observing cosmic phenomena, we'd be borrowing their tricks. Then there's the wildest possibility: black hole archaeology. Primordial black holes from the early universe could contain perfectly preserved quantum snapshots of the Big Bang's first moments. If we ever retrieve that data, it would be like finding the universe's birth certificate, complete with details about dimensions we can't perceive and forces that faded eons ago. Some theories even suggest advanced civilizations might use black holes as ultimate time capsules, encoding knowledge in event horizons to survive cosmic endings. Of course, these ideas dwell in speculative territory for now. But history shows that today's impossible dreams become tomorrow's tools. Radio waves were once curiosities, now they connect the planet. Nuclear fusion, once only a solar process, might soon power our cities. Similarly, understanding how black holes safeguard information could spark a revolution we can barely fathom. The paradox isn't just a puzzle, it's a portal. And on the other side waits a future where we don't just understand the cosmos, but converse with it in its native tongue. At the heart of the black hole information paradox lies a question that rattles the foundations of physics. What if information isn't just a byproduct of reality, but its very essence? We're used to thinking of the universe as built from matter and energy, tangible stuff we can measure and observe. But the paradox forces us to consider a radical alternative. Information might be the bedrock of existence, with particles and forces merely its shadows. Imagine a cosmic symphony where the notes themselves are secondary. The true music is in the sheet music, the abstract relationships between them. Black holes, in their relentless swallowing and potential regurgitation of data, could be showing us that the universe isn't just described by information, it might be information. This idea isn't entirely new. Philosophers and physicists have long toyed with the notion that reality is fundamentally mathematical, a network of logical relationships rather than solid stuff. But black holes add urgency to the debate. When matter vanishes beyond an event horizon, what remains isn't just memory or residue, it's a precise encoding of quantum states on the horizon surface. The fact that this encoding seems to preserve every detail of what fell in, like a cosmic QR code, suggests information isn't merely recorded by the universe. The universe might be the recording. Think of it this way: a novel isn't just ink on paper. The ink could fade, the paper crumble, but the story persists as long as its information is preserved elsewhere in a digital file, a memory, even carved into stone. Similarly, a black hole's contents might exist not as particles trapped inside, but as patterns etched into spacetime's fabric. This shift in perspective turns the paradox on its head. We've been asking how information escapes black holes, but what if the real question is why we ever thought it was trapped to begin with? Perhaps black holes don't hide information. They reveal its primacy by stripping away the illusion that matter and energy are the main actors. The implications ripple far beyond astrophysics. If information is fundamental, then reality might operate like a vast computation, with black holes as its most extreme processors. Quantum bits entangled across spacetime, holographic projections, even the apparent flow of time, all could emerge from deeper informational rules we've yet to decode. Skeptics argue this veers into metaphysics, but the math is increasingly hard to ignore. From quantum teleportation to error-correcting codes in Hawking radiation, the universe keeps hinting that its true language isn't force or mass but data. What's humbling and exhilarating is how the paradox exposes our biases. We're creatures of a middle world, evolved to perceive objects and collisions, not the hidden code underlying them. Black holes, in their brutal simplicity, force us to confront that blindness. They're not just cosmic puzzles, they're mirrors reflecting back the limits of our intuition. And if staring into that abyss teaches us anything, it's that reality might be far stranger, far more elegant than we ever dared dream. The information paradox isn't just a physics problem, it's an invitation to rethink what exists even means. While mainstream physics wrestles with holography and quantum resets, some theorists venture into even wilder territory, where black holes aren't just cosmic objects but glitches in reality itself. Take the simulation hypothesis. If our universe is an artificial construct, black holes could be data compression points, cosmic garbage collectors recycling unused information to free up processing power. In this view, the event horizon isn't a physical boundary but a firewall preventing resource-hungry simulations from rendering infinite density, like a video game deleting assets that fall out of bounds. The information paradox would vanish not because information escapes, but because it was never truly lost, just archived in the universe's source code, waiting to be reloaded if needed. Then there's the mind-bending idea that black holes are literal portals, not just to other regions of space, but to entirely separate universes with different physical laws. This isn't just sci-fi speculation. Mathematical models in loop quantum gravity suggest singularities might bounce, transforming collapsing matter into a big bang for a newborn cosmos. Imagine tossing a rock into a pond, except the ripples don't fade, they surge outward as an entirely new pond. In this scenario, the information swallowed by our black hole doesn't scramble. It becomes the building blocks of another reality with its own spacetime and quantum rules. The paradox dissolves because the data isn't destroyed, it emigrates. Even stranger are theories invoking time loops. Some interpretations of general relativity allow for closed time-like curves, paths where time circles back on itself near a black hole's core. Information falling in could be trapped in an infinite echo, cycling endlessly between past and future states. To an outside observer, it's gone forever. But in reality, it's stuck in a cosmic holding pattern, like a DVD skipping on the same frame. This wouldn't violate quantum mechanics' no deletion rule. The data still exists just outside conventional time. Skeptics dismiss these ideas as untestable metaphysics, but their value isn't in proof, it's in perspective. When mainstream theories hit walls, radical alternatives force us to question assumptions we didn't even realize we'd made. Maybe black holes aren't objects to be dissected, but symptoms of deeper truths, cosmic breadcrumbs leading us toward a grander architecture of reality. Whether glitches, portals, or time machines, they remind us that the universe's strangest corners might demand stranger tools to understand. And sometimes the most outrageous ideas are the ones that crack the code. Decades of debate and discovery have brought us closer to solving the black hole information paradox, yet the cosmos stubbornly refuses to surrender its final answer. Most physicists today lean toward a compromise. Information almost certainly isn't lost, but how it escapes or whether it was ever truly trapped remains hotly contested. The majority view crystallized after Hawking's famous concession in 2004, when he abandoned his earlier stance and admitted black holes likely preserve data in some form. Since then, the holographic principle has emerged as a leading framework, with heavyweights like Leonard Susskind and Gerard T. Hooft arguing that event horizons act as quantum hard drives, encoding swallowed information in their two-dimensional surfaces like cosmic QR codes. Yet consensus stops there. Scratch beneath the surface and you'll find a spectrum of interpretations. Some researchers champion string theories, fuzzballs, where black holes are tangled yarn balls of vibrating strings with no interior void to trap information. Others advocate for subtle quantum resets at singularities or entanglement bridges woven through spacetime. Even the firewall paradox, once seen as a fringe idea, still has staunch defenders who argue that smooth event horizons might be mathematical mirages. What unites these diverse views isn't a shared solution, it's the shared conviction that quantum mechanics' core tenets must hold. Destroying information would unravel the foundation of predictability in the universe, making the past as uncertain as the future. The closest thing to middle ground, a grudging acceptance that any resolution will require rewriting our understanding of spacetime itself. Whether through AdS/CFT's holographic duality or emergent gravity models, physicists increasingly suspect that locality, the idea that objects exist in specific places, might be an illusion. Information could be simultaneously inside the black hole and smeared across its horizon, with no single perspective capturing the full truth. It's as if reality employs a cosmic version of duck typing. If something walks like quantum information and quacks like quantum information, it doesn't matter where it really is. Despite the lack of a smoking gun proof, progress is tangible. Gravitational wave astronomy, quantum simulations, and even tabletop black hole analogues are testing once untouchable hypotheses. The paradox has become less a wall and more a sieve filtering out ideas that can't reconcile quantum mechanics with gravity. Until experiments or math deliver a knockout blow, the field remains vibrantly pluralistic. And perhaps that's the lesson. Sometimes the universe teases us with questions so profound that the hunt for answers reshapes science itself along the way. The next frontier in solving the black hole information paradox isn't just about theories, it's about tools. Enter LISA, the Laser Interferometer Space Antenna, a revolutionary gravitational wave observatory set to launch in the 2030s. Unlike ground-based detectors like LIGO, which listen to the collisions of stellar mass black holes, LISA will float in space, free from Earth's vibrations, with laser arms spanning millions of kilometers. This colossal scale lets it detect lower-frequency ripples, the kind emitted by supermassive black holes merging at the hearts of galaxies. These cosmic monsters, millions of times heavier than the Sun, warp spacetime so profoundly that their gravitational waves could carry subtle imprints of quantum effects near their horizons. If information leaves fingerprints in spacetime, LISA might be the first to catch them in the act, but gravitational waves are just one piece of the puzzle. Down here on Earth, quantum simulators are recreating black hole physics in labs, using ultra-cold atoms, superconducting circuits, or even light pulses to mimic event horizons. These aren't mere analogies, they're controlled experiments where scientists can tweak parameters impossible to observe in nature. A team at the University of Maryland recently simulated a black hole's entanglement dynamics using ytterbium ions, observing how information might scramble across an artificial horizon. Meanwhile, others are exploiting quantum hair, the faint gravitational imprints left by particles, to track how data leaks into Hawking radiation. It's like reverse engineering a locked safe by building thousands of miniature versions until you find the combination. Then there's the Event Horizon Telescope's next leap. After capturing the first image of a black hole's shadow, the collaboration is expanding, adding more telescopes to sharpen its vision. Future observations could reveal flickers or distortions in the glowing accretion disk, hints of quantum turbulence near the horizon. Combine this with data from neutrino observatories, which catch particles spat out by black hole jets, and suddenly we're not just staring into the abyss, we're mapping its hidden currents. The most audacious experiments lie in tabletop quantum gravity. Researchers at Imperial College London are probing whether spacetime itself is pixelated by firing lasers at supercooled diamonds, hunting for minuscule delays that might betray a quantum foam structure. Others propose using quantum memory devices to track how information scrambles in simulated black holes, looking for telltale patterns that mirror theoretical predictions. These projects sound like science fiction, but they're grounded in a simple truth. If we can't travel to a black hole, we'll bring its mysteries to us. What unites these efforts isn't just technology, it's a shift in philosophy. We're no longer waiting for a lone genius to scribble the answer on a chalkboard. Instead, we're building an arsenal of instruments, from space antennas to quantum circuits, each designed to corner the paradox from a different angle. Whether through gravitational whispers, lab-grown horizons, or pixelated spacetime, the message is clear: the universe's darkest secrets won't stay hidden forever. And when they finally emerge, they might rewrite not just our understanding of black holes, but reality itself. The black hole information paradox isn't just a puzzle, it's the ultimate Rosetta Stone, a cosmic cipher holding the key to unifying physics' greatest theories. Like a language bridging ancient civilizations, this paradox connects the realm of the impossibly small, governed by quantum mechanics, with the domain of the unimaginably vast, ruled by general relativity. For decades, it's forced physicists to confront the uncomfortable truth: our understanding of reality is incomplete. but in that incompleteness lies extraordinary opportunity. Every proposed solution, from holography's encoded surfaces to fuzzballs' vibrating strings, from entanglement's hidden bridges to baby universes budding in the dark, isn't just an answer. It's a glimpse into a grander framework, a theory of everything waiting to be born. What makes this paradox so powerful is how it strips away our assumptions. We've long imagined black holes as cosmic trash compactors, but what if they're more like transformers, reshaping information rather than erasing it? The debate has birthed ideas that sounded like fantasy, space-time holograms, firewalls, quantum resets, yet each emerges from rigorous math, pushing the boundaries of what we thought possible. And that's the paradox's true gift. It doesn't just challenge our knowledge, it expands our imagination. Whether information escapes, lingers, or transcends, the answer won't just solve a mystery, it'll redefine existence itself. So here's the question that leaves even physicists awake at night. Which solution resonates with you? Do you see black holes as cosmic archivists, their horizons etched with quantum blueprints? Or as quantum alchemists transmuting matter into new universes? Maybe you're drawn to the wild card, that space-time is a code we've yet to crack, and black holes are its debug logs. The beauty is we're all part of this discovery. Every observation, every experiment, even every spirited debate in comment sections nudges us closer to truth. So share your thoughts below, because the next breakthrough might not come from a lab or a chalkboard, but from a conversation that sparks the right idea. After all, the rules of reality aren't just written in the stars, they're waiting to be rewritten by those daring enough to question them.